Hi everyone. Today our group will present our Advancement 2 project, Lights Out, Data On, and forecasting Formula One podiums and championship points. And I'm Hao Minqi, and my teammates including Xu Si, Feng Fei, and Han Yu. And here's the outline of our talk. And so let me start with our part one, predictive task and evaluation. So Formula One is the top level of open rail racing around the world, and each year there is a world championship with many races around the world. And every race weekend has a qualifying, which sets the start grades and then the main race. Race results give the both points with drivers and teams called constructors. And only the top 10 finishers get points, and the podiums is the top three of each race. Performance depends on many factors: the drivers, the cars, the team, circuits, weather, and the rules of the area. And our goal is to capture some of these effects with data. So our project uses the real F1 data to study two predictive tasks. And task one is to predict which drivers will finish on the podiums in a given race. And task two is to predict each driver's final championship points from the mid-season information. And we combine simple frequency-based baselines with classical models from this class, such as the logistical regression and the linear regression, and to see how much structures we can capture with a relatively simple method. So let me define the two tasks more clearly. For task one, the unit is one driver before one race, and we want the probabilities that drivers finish in the top three for that race. For task two, the unit is one driver in one season, and I want to predict that driver's final championship point at the end of the season. And for these tasks are complementary, actually. Task one focuses on the single race outcomes, while task two focuses on the long-term season performance. So for task one, podium prediction is both binary classifications and within race ranking problems. And we use the ROC, UC, and F1 scores to measure how well we separate podiums and non-podium drivers overall. And we use the required three and top one accuracies to evaluate the ranking quantities, and whether our top three match the real podium, and whether we correctly predict the winner. And our baseline, including global driver circular constructor, and the historical podium frequencies, etc. And then we're training the logistical regression model using grid, pre-racing form, racing result, and the race day weather as features. And for task two, season points are treated as both the regression and the ranking problems. We use the MAE and the RMSE to measuring the point prediction error, and R square to show how much variance in final points we explain. And baselines, including simple means such as the global and driver-specific average, are used the strong midpoints baselines that simply predict the final points with the mid-season points. And also considering the areas and the constructor means, including structures times with the weather buckets. And finally, we feed it with the linear regression model with the mid-season points, season year, constructors, and the season average weather. And so next, let me move to the part two of the data processing. And before the raw data, let me explain how well we keep the evaluation realistic. And we adopt the temporary slip for training, validation, and test data sets. So we always predict the future races from the past data. And we compare against the intuitive baselines, grid only for task ones and midpoints for task two. And we use a multiple matrix across the classifications, regressions, and ranking to avoid overfitting into a single score. Our data comes from two local data sets, both official. And the first is the F1 World Championship data set from 1950 to 2024, covering races, results, drivers, and more. And second is the F1 weather information data sets, which provides the weather features for each race. And in this project, we restricted to seasons from 2000 to 2023, focusing on the morning era where scoring, calendars, and weather records are more stable. So we process the raw CSV files into two clean task data sets. From the core F1 data, we use the tables such as races, results, driver standings, and constructors. And from the weather data, we use the weather feature V4, which consists the temperatures, precipitations, and the wind speed for each race. For task one, we build one row per race and drivers with labeled podium. And for task two, build one row per year and driver, storing both the midpoint and the final point. And these process the CSVs fitting directly into our baselines and the modeling scripts. And for task one, feature including grid position, year-round circuits per racing point and ranking, etc. And for task two, features including mid-season points, year constructors, and the season average weather. And after fitting to certain years, task one has about 5K train, 1.6K validation, and 2K test samples. Task two has roughly about 300 train, 86 validation, and about 100 test driver seasons. And our analysis shows that the midpoints and grid has already provided very strong signals, and our baselines and models built on the top of these patterns. So with these setups, let me partner Xu explain more about the modeling part.
Okay, let me explain with the modeling part. So first, let's define our machine learning problem. The task one is podium prediction. We treat this as a classification and ranking problem. Given the grid position and driver history, what is the probability that a driver finishes in the top three? We optimize for log loss to ensure the calibrated probabilities. Task 2 is season points prediction, a regression task. Use only data up to mid-season. We aim to forecast the final point. Here, we optimize for mean absolute error to handle outliers effectively. We start with common sense baselines to establish a performance floor. For task 1, our first try is consider about the grid position is related to finish position. We also train a logistic regression. While it improved accuracy, it suffered from a critical theoretical flaw, the independent assumption. It treats every driver as an isolated data point and ignoring that racing is a zero-sum game against the specific opponents. For task 2, we use a linear regression on aggregate statistics, and it captured the general trend but failed to predict the late season comebacks as it ignores momentum. For task 1, we use two-head fusion as an improvement because podium and winning are totally different signals. Podium shows consistent race-long performance, but winning is a rare sharp event. One model can't learn both well, so we trained two simple heads, a podium head for overall competitiveness and a winning head for front-running situations. Then we use a small 3+1 explanation rule to catch extra upset winners. Finally, we fuse both calibrated scores, giving a winner prediction that's more stable and accurate than either head alone. This is a code about two-head fusion. It includes the prediction, 3+1 strategy, and the fusion logic. The next improvement is XGBoost. To overcome the rigidity of linear models, our improvement was XGBoost because F1 data is highly non-linear. The difference between the starting first and third is massive, but the difference between start 15th and 17th is negligible. So the tree-based model naturally learned this threshold. Furthermore, XGBoost ultimately captures features interactions, so it is great to solve this problem. And this is a code base for gradient boosting. It includes the handling the class imbalance and the modeling initializations and training validation monitoring. For task 2, we use the MLSP as an improvement. Our minimal linear season predictor simply enriches mid-season stats with a few normalized rates and two tiny interaction terms. This fix makes the model stable across eras and let it capture basic non-linear effects that the baseline linear regression misses. With just these minimal additions, we get a clear boost in final points prediction without adding any complexity. And the code includes two main parts, which is normalization and interaction terms. And there's another improvement using transformer. We call it context-aware transformer. We reach out our solution because this represents a paradigm shift from point-wise to list-wise prediction. In F1, you don't race in a vacuum, you race against specific opponents. If you are P3, your chance to winning depends heavily on whether P1 is strong or made field car in a lucky position. The transformer uses self-attention to capture this driver-to-driver interaction explicitly. And here is the architecture of the transformer. Yeah, that's let Fengfei for continue with the evaluation part.
Now I will be presenting the evaluation section for this project. We access our models across two different tasks, ensuring that performance gains are both statistically significant and relevant to the F1 sport. Our evaluation framework is divided by the task nature. For the task 1, race podium prediction, we require both global classification and specialized ranking metrics. We use ROC-AOC and F1 score to measure the overall classification and discrimination abilities across all driver race samples. Crucially, we use recall at 3 and top 1 champion accuracy. These specialized metrics quantify the actual heat efficiency on the high-value positions, such as top 3 and champion, within a single race, which is our core business objective. We establish the logistic regression as the trivial baseline for the task 1. This baseline achieved an initial ROC-AOC of 0.88 and a recall at 3 of 58%. However, its low top 1 accuracy, which is 33%, confirms that the current features are insufficient for predicting the final winner. This demonstrated the urgent need for a feature-rich model. To address this, we developed two methods. The first one is two-head fusion, which uses separate logistic regression heads for podium and winner, leveraging features like weather and interaction terms, along with a conditional 3 plus 1 fusion strategy. The second one is gradient boosting, aims to introduce nonlinearity and directly optimize for ranking aware loss functions, breaking the linearity ceiling. Comparing the baseline against our advanced methods, the improvement is substantial. The first method boosted the global ROC-AUC by around 0.05 and increased the recall at 3 to 68%, validating the power of our architecture. Besides, we improved the top 1 accuracy up to 53%, as we can see from the table. Method 2 achieved even better performance over the 4 metrics. Technically, the implementation of our evaluation protocol used a custom recall at 3 and top 1 accuracy calculation after sorting predictions by probability, ensuring our results are relevant to the real-world ranking scenarios. For the task 2, season final points prediction, our regression task, we use MAE and RMSE to quantify the numerical accuracy of point prediction, where MAE for average error and RMSE for penalizing large errors. We also use R squared to measure the overall numerical fit and the Spearman rank correlation to ensure the accuracy of the final relative standing order. For task 2, the linear regression baseline achieved a near-perfect Spearman of 0.97. This immediately highlights that the ranking order is highly stable early on. The core challenge is minimizing the high numerical error with an MAE of 55 and an RMSE of 84. We tackled this with two methods. The first one is minimal linear season predictor, leveraging an enhanced feature set to maximize the numerical fit. And the second one is context-aware transformer, which is designed to capture the dynamic dependencies and the entire sequential nature of the season, aiming to break the high R-squared ceiling. Comparing the baseline with our advanced methods, the performance leap is dramatic. For example, method 1 reduced the MAE from 55 to 15 and RMSE from 84 to 23, a 70 percentage reduction in numerical error. Furthermore, it achieved an R-square of 0.96, proving the exceptional quality of our full feature set. Similarly, method 2 showed superior performance over the 4 metrics than baseline. Technically, we directly use scalar functions as our evaluation functions for MAE, RME, RMSE, and R-square, as shown in the code scripts.
Now I will move to part 5.
I will talk about related work, F1 and sports outcome prediction. In F1 analytics, most work uses logistic and linear regression on grid, team, and racing points. Many Kaggle projects basically say good grid and strong team to get high podium chance and treat each driver race independently. In other sports, people use ELO and true skill position models and later GPT plus learning to rank for match outcomes and standings. The earliest FRA data we use is common, but mostly for single race prediction or descriptive plots, not for joint treatment of podiums plus season points. Extending classical sports models. Our first step is to upgrade these classical models. MLSP is a linear season model with 3 features and a few interactions, designed to stay robust across scoring areas. Race level SGBOS is a GBDT podium classifier that handles class imbalance and is third for AUC recall at 3 and top 1, giving a stronger non-linear baseline. Two-head fusion and over-positioning. Modern ML often uses ensamples and multi-head architectures. We follow this idea with two-head fusion. One head targets overall podium recall, the other targets winner prediction, and a simple 3+1 expansion plus soft fusion balances don't miss prize winners with stable podiums. Overall, our work sits between classical sports analytics and context-aware deep models, combining interpretable linear GBDT baselines with a race context transformer and two-head fusion. Context-aware ranking and transformers. In deep ranking, transformers are widely used for list-wise recommendation and click prediction, and set-based segmentation captures interactions within a set of items. We adapt these set-based transformer ideas to F1 race grids, modeling intra-race competition instead of scoring drivers independently. Consequently, we move from deep ranking to set-based models to F1 grids. How our results compare to prior work. Our results match prior past findings that grid and team are very strong signals, and that season-long rankings are more stable than single race outcomes. At the same time, we see that high ROC and AUC can still have poor recall at 3 and top 1, so ranking metrics are essential. Finally, race context transformer plus two-head fusion beat grid only and independent GBDT models on both recall at 3 and top 1. And our rate feature baseline stayed stable across different scoring areas, which many earlier analyses don't address.
Yeah, that's everything for our presentation. Thank you all for listening.